Hello everyone, welcome to my lecture series of electromagnetic fields. We will discuss different theories, phenomena and numerical solution of different cases in this series. I hope this series will give a fruitful outcome to physics scholars or engineering students. Up to the last part of this lecture series, we have discussed dot product and cross product of vectors. To verify that part, please click I button on your screen. Today, we are going to discuss triple product of vectors, in which we will see scalar triple product and vector triple product. So both these algebraic operation on vectors are very important as far as the vector calculus is concerned. So let us see scalar triple product. So the scalar triple product is the dot product of three vectors, and it represents the volume of parallelepiped spanned by that three vectors in the space. It has a very limited physical applications, but it is widely used in solving vector complex problems of calculus. So let us understand what exactly is the scalar triple product is. So consider three vectors a bar equals to ax bar plus ay, that is y coordinate of vector ay bar plus az bar, and similarly we have defined vector b and vector c. As the name suggests, it is a triple product. That means we are going to use three different vectors. Fine. So these three vectors, let us say we can draw that vector in a space. So a bar I have shown in a horizontal axis, b bar is on xy plane but going to negative x direction, and c bar is on yz plane but with some angle phi. Fine. So you can represent any three vector, fine, but this is just for an example. So for any three vectors which are forming some angles between them, then its scalar triple product is defined as a bar dot b bar cross c bar equals to determinant of the 3 cross 3 matrix, in which first row represents the x, y and z coordinate of first vector, second row represents the x, y and z coordinate of second vector, and third row represents the x, y and z coordinates of third vector. Now here it is scalar triple product, but we cannot show this like a bar dot b bar dot c bar, because this is not a triple product, because b bar dot c bar will give you a constant or a scalar, and again if we multiply any constant with vector, then it is scaling, it is not dot product. Fine. So for dot product we need two vectors on both the side of dot. So a bar here, as you can see, is a vector a. In right hand side of this dot sign we must need another vector. Fine. So that is why we cannot put dot over here, but if we do a cross product of b bar and c bar, then its result will also be a vector. Fine. And as I have stated in the starting of this lecture, that this dot product represents the volume of this parallelepiped. Fine. First we will see how this equation has been arrived, and then I will prove that how this dot product defines a volume which is spanned by these three vectors. Okay, so let us begin. So the definition of dot product or scalar triple product is a bar dot b bar cross c bar. Now if we simplify it, so we can write a bar as it is. Now b bar cross c bar will be a matrix determinant whose first row represents the base vector of coordinate system, second row represents the x, y and z coordinate of first vector. Here our first vector is b bar for that particular cross product, and third row will represent x, y and z coordinates of second vector. Now simplifying this determinant, we will have a bar dot by cz minus bz cy ax bar. Okay, we will keep it in a square bracket because three terms will be there, plus bz cx minus bx cz ay bar plus bx cy minus by cx a z bar. Now if we apply this dot product with all these terms, then a bar, we know that a bar can be written as ax into ax bar plus ay into ay bar plus az into az bar dot, this same square bracket will come here. Now we know that only ax bar dot ax bar will be 1, ax bar dot ay bar and ax bar dot az bar will be 0, so we need not to calculate the multiplication of these two terms with ax bar term. Then in second step, only ay bar dot ay bar will be 1, ay bar dot ax bar and ay bar dot az bar will be 0. So again we need not to multiply three different terms, we need to multiply just one term. Fine. So doing so, I have ax into by cz minus bz cy plus ay into bz cx minus bx cz. You may also try this calculation on your own because it will be very tedious if I write each and every term over here. And third term will be az into bx cy minus by cx. And we have alternate arrangement of this representation, so we can represent these three terms in terms of matrix as ax, ay, az. Then the cofactor of ax, it will be bx cz minus bz cy, so we can arrange it like by and cz. Then minus, so we need not to put any minus sign in either of these two elements, we will simply write bz cy. Then for ay we have bz cx minus bx cz, so we can simply write bx over here and cx over here. So if you find the determinant of these 3 cross 3 matrix, then you will certainly got this result. Fine. So hence we have seen how the scalar triple product is defined mathematically. Now let us see how does it shows the volume of that parallelepiped which is formed by these three vectors. So for the simplicity, I am going to draw a cube. So I am drawing a cube with length and height equal to 3 units. So as you can see, the front face of my cube is having a length of 3 units and a height of 3 units. Now I am defining the depth of this parallelepiped as 1 unit. So the depth of my parallelepiped is 1 unit. And if I complete the whole parallelepiped, then we will get this kind of shape in three-dimensional space. Okay, now if I use some vector representation, so I am keeping the back corner of this parallelepiped as origin. So I am treating this point as origin, and I will represent the whole parallelepiped with the help of three vectors. So the first vector which I am going to utilize will lay on x-axis. Fine. So what is the length of this vector? The length of this vector is 3 unit. And what is the direction? So it is in the direction of x, so I can write ax bar. Let us say it is our first vector a bar. Fine. Then second length, that is the depth of this parallelogram. I am defining the depth in form of vector by z-axis. Fine. So what is the length of this line or depth of this parallelogram? So it is 1 unit. And what is the direction? Az bar. So we can represent this as 1 into az bar. Let us say this is our third vector c bar. And let us now represent the height of this parallelogram or parallelepiped on vertical axis or y-axis. So what will be the length of this vector? Now this vector has a length equal to the height of parallelepiped, that is 3. What is the direction? In y direction, so 3 ay bar. And let us say this is our second vector b. Now using the geometrical formula for the volume of any parallelepiped, so geometrical formula for the volume of any parallelepiped. So we all know that volume of parallelepiped is nothing but the multiplication of length into height into depth or width. Fine, here we have defined depth. So length is 3 unit, height is also 3 unit, and depth is 1 unit. So the volume will be 9 unit cube. This unit may be anything, centimeter, meter, anything. Fine, but the volume of this parallelepiped is 9. So if we say that scalar triple product of any three vector defines the volume of parallelepiped, then doing so, if I perform scalar triple product on these three vectors, so a bar dot b bar cross c bar, which is nothing but ax, ay, az, bx, by, bz, and cx, cy, cz. So the x component of a is 3. The y and z component of vector a is 0. So we will put 0 simply. Then the x component of b bar is 0. Same way the z component of b bar is also 0. Only the y component is there, which is 3. And for vector c, its x and y components are 0. Only z component is non-zero, which is plus 1. So we will put. So we have got one diagonal matrix, and now the determinant of this diagonal matrix is the multiplication of its diagonal terms. So 3 multiplied by 3 multiplied by 1. So 3 by 1 multiplied by 3. So we will have 9 unit cube. So hence we can say that scalar triple product of any three vectors represents the volume defined by volume of parallelepiped defined by those three vectors. Fine. So the physical application of such scalar triple product are very less, but whenever we are going to have some calculations where complex vector algebra or vector calculus will be there, at that time this equation will be very helpful for us to simplify any complex equations. Moving further, the scalar triple product depends on the cyclic order of the vectors and not on the position of dot or cross in the product. What does this statement means? That as the dot product is following the law of commutation, we can say a bar dot b bar cross c bar equals to b bar cross c bar dot a bar. Fine. And if we follow the cyclic order, then it will also say we define a cycle like a bar, b bar and c bar. Then if we follow the same cycle either clockwise or anti-clockwise, then it will be very same. So this a bar dot b bar cross c bar will also be equal to b bar dot c bar cross a bar. It will also be equal to c bar dot a bar cross b bar. But what is not allowed in this equation, that if we write a bar dot b bar cross c bar, so it will not be equal to a bar dot c bar cross b bar, because cross product does not obey the law of commutation. Fine. So these two quantities will be different, but these four quantities will be the same. So as far as you are following the cyclic order of the vectors, there will not be any change in the value of scalar triple product. Secondly, if two of three vectors are equal, then result of such scalar triple product will be 0. It is also a very popular property of matrix determinant. Then for any matrix, if two row, here for 3 matrix we will have 3 rows in our matrix. So if two rows are equal, that R1 equals to R2 or R2 equals to R3 or R1 equals to R3, if any of these three conditions will be there, then always the determinant of such matrix will be 0. Fine. So if two vectors of 3 are equal, then its scalar triple product will always be 0. Fine. Because here if two vectors are equal, then there is no parallelopipe formed in the space. Fine. Only parallelogram will be there, and volume of parallelogram is 0. Fine. So we can also understand this line by the physical meaning of scalar triple product. Then scalar triple product is distributive. Fine. So you can also solve the same, that is a bar dot b bar dot cross c bar. You can also do it by finding a bar dot b bar and multiply it by a bar dot c bar. Fine. So in that case it is distributive. Fine. Now the next topic of today's lecture is vector triple product. So the vector triple product of three vectors a bar, b bar and c bar defined same as we have previously defined. So this mathematical operation or vector algebraic operation is defined as a bar cross b bar cross c bar equals to b bar scaled by the dot product of a bar and c bar minus c bar scaled by the dot product of a bar and b bar. Fine. Now due to the representation of this equation, this is also known as back-cap rule. Fine. So here back stands for BAC, dash stands for minus, and CAB. Fine. Due to the appearance of this formulae, this triple product is also known as back-cap rule. Fine. So the position of these brackets are very important. Fine. So ultimately vector triple product of three products will give us vector result. That is why it is named as vector triple product. but this result does not show anything physically about the system in which these three vectors are lying. Fine. So we will not able to discuss the physical meaning of vector triple product. However, it will guaranteedly reduce our computations. So if we want to perform two cross products among three vectors, then it will be comparatively easier to use this formula rather to calculate the cross product twice. Fine. So it will give us very much benefit in case of calculations. Now we will try to prove that how A bar cross B bar cross C bar equals to B bar A bar dot C bar minus C bar A bar dot B bar. So we will do it very quickly. So first we will find RHS of above equation. So A bar dot C bar. So in place of B bar we can write BY bar plus BZ AZ bar. The dot product of A bar and C bar will be AX CX plus AY CY plus AZ CZ minus C bar can be represented as CX AX bar plus CY AY bar plus CZ AZ bar, and dot product of A bar and B bar can be written as AX BX plus AY BY plus AZ BZ. AX BX CX plus AX AY we will try to keep the sequence of A, B and C so that we should not worry about the final result. So it will be like this plus AX BY CX plus AY BY CY plus AZ BY CZ AY bar plus AX BZ CX plus AY BZ CY plus AZ BZ CZ AZ bar. Now same mathematical operation will be carried out for second term. So after applying minus sign to each, we will have AX BX CX plus AY BY CX plus AZ BZ CX AX bar plus, sorry, not plus, here it will be minus because we will simultaneously apply the minus sign to each term. Okay, so we will have AX BX CY plus AY BY CY plus AZ BZ CY AY bar minus AX BX CZ plus AY BY CZ plus AZ BZ CZ AZ bar. Now what we will do, we will separately operate the coefficients of AX, AY and AZ, and finally we will have AY BX cy minus ay by cx minus az bz cx plus az bx cz ax bar. It is quite tedious, quite complex, fine, but it is just for your reference that how can we prove that vector triple product is exactly equal to the back cap. Our y coordinate of resultant triple product will be az by cz minus az bz cy minus ax bx cy plus ax by cx ay bar plus z coordinate will be ax bz cx minus ax bx bz minus ay by cz plus ay bz cy az bar. Fine. Here also you can see that ax bx cx will be cancelled out from here. Ay by cy will be cancelled out from here due to negative sign. Same way az bz cz will be cancelled out from here. So two terms with positive sign and two terms with negative sign will be there in each coordinate of x, y and z. Fine. So we will keep this result as 1. Now we will try to calculate the left hand side of the equation. So the left hand side of the equation states a bar cross b bar cross c bar. So we can have a bar cross. Now the result of this b bar cross c bar will be ax bar, ay bar, az bar, bx, by, bz, cx, cy, cz. Fine. So you will get a bar cross by cz minus bz cy. You can perform this operation on your own, fine, and also let me know if you have some difficulty by solving this. Actually it is very easy, it is just quite cumbersome job to perform. Bx cy minus by cx az bar. Now if we perform the cross product of this term with a bar, then it will be the matrix determinant of, again we will write ax bar, ay bar, az bar. The second row will be ax, ay, az, and third row will be by cz minus bz cy, then bz cx minus bx cz, and third will be bx cy minus by cx. Now if you find the determinant of this matrix, then you will get ay bx cy minus ay by cx minus az bz cx plus az bx cz ax bar plus az by cz minus az bz cy minus ax bx cy plus ax by cx ay bar plus ax bz cx minus ax bx cz minus ay by cz plus ay bz cy az bar. So once you come to up to this point, then you can verify that this value of left hand side and the value that we have calculated of right hand side of this equation both are same, and hence we can say that vector triple product of three vectors can be defined as scaling of second vector with the dot product of first and third vector minus scaling of third vector with the dot product of first and second vector. Fine. Otherwise you may also remember this equation with this back cap rule. Fine. Thank you.